So today I will tell you, I give more or less an overview, but with some details about my research. And I decided to go quite a long time back and hopefully have a story on how I started and more or less what I am doing now. So in a nutshell, what we do in my group is we turning waste on one hand into advanced materials that are then used for electrodes in batteries, in particular those batteries that go beyond lithium ion and are more sustainable, but also we work a lot in developing new and critical metal-free catalysts for fuel cells. And on the other hand, we also more recently have a great interest in turning this waste directly into hydrogen and chemicals. And we do this, of course, in our global effort to hopefully solve the climate crisis. And of course, the idea is to try to secure new technologies that are cost and energy efficient. But at the same time, when we do that, we need to pay a great attention to where exactly the security of the supply chain will come for, what materials are we going to use to build those new technologies so that actually we have zero carbon emissions. So I will start with the process that I discovered many years ago, about 20 years ago, when I was actually a postdoc in Germany at the Max Planck Institute of Colloids and Interfaces. And the story goes a bit like this. During my PhD, I was working on completely different things that I'm doing now. So I was an expert in developing some very tailored polymers that would selectively recognize certain molecules. So then following in my postdoc, my job was based on this expertise on developing these polymeric membranes that were particularly selective to a certain component, was to turn biomass into high-value chemicals and try to develop very molecular selective membranes to fish these molecules out of the aqueous phase. So the idea was to make high-value chemicals such as hydroxymethylfurfural and levulinic acid through processes of different biomass or biomass derivatives. However, when I started doing this in my postdoc, I realized that every time I was doing an experiment, I was getting black precipitates at the bottom of my reactor. So then I became very interested in what exactly these black precipitates are. And so instead of really doing my project, I started looking at these black precipitates. And I don't know how many very early careers are here, but if they are, I guess the message is that if you come across something unusual in your research, despite that that's not the main line of your research, you should really pursue it because it may change your career and definitely change mine because that's how I got into carbon materials. So what's happening here with biomass is that through a process that's similar to the natural coal formation, but rather than waiting hundreds of millions of years, you just wait about a few hours, you can turn biomass into carbon. And it does this with some heat, but not too much heat, about 200 degrees, and under self-generated pressure that are between 30 and 50 bars, depending on the loading, the conditions that you work. So basically, through this process that then I call the hydrothermal carbonization process, you get three things at the same time. You take biomass precursors that is actually rich in carbohydrates, and I'll come back to this, and you turn it into these black precipitates, and then this you can then nanostructure using materials chemistry tricks, and you get carbonaceous materials. So a lot of nanostructure carbons that form here at the bottom. Then once you filter this out, you end up with an aqueous solution, which is what I was supposed to do. And in these aqueous solutions, you do find a lot of valuable chemicals, hydroxymethylfurfural, levulinic acid, and so on. And so if you could separate this, but it's very difficult, and actually I've never managed to do it, you can then transform this into other useful chemicals or even bio-based polymers or fuels. Now, interestingly, in the interface between this aqueous phase and the solid phase here in this reactor, you also have a phase that contains these tiny dots that are known in the literature under the name of carbon dots. These are very complicated, very ill-defined nanomaterials that can exhibit fluorescence. So I've been also spending some time trying to understand these carbon dots, particular their structure, why do they fluoresce, how the fluorescence properties correlate with their chemistry, and then also we've tried to use them in photocatalysis, but not as photocatalysts themselves, but rather in conjunction with other semiconductors to change the band gap. But of course, today I won't have time to tell you about this. I will stick with the nanostructure carbons, in particular their applications. But now coming back to these carbon materials, the way it works is that you need to have a lot of carbohydrates. So we, back in the time that I was a postdoc, and then because of this technique, I was then got an independent fellowship at the Max Planck Institute. I've been looking a lot at the fundamentals of this hydrothermal carbonization process, how these particles form, what is their chemical structure, and so on. So of course, this is an oversimplification, but in general, the nice thing about this is that you get monodispersed spherical particles from this hydrothermal carbonization. So I call this a bit the sol-gel process of carbon, because you can do this in water, and by doing this in water and working with soluble precursors, which I started to work, such as glucose, chitin, chitosan, cellulose, hemicellulose, pure precursor, you can then play around with templating, hard templates, soft templating, and other things to make nanostructure carbon, a bit as you do in inorganic synthesis of metal oxides. So as I said, it helps to have carbohydrates, and that's because if you look then at the chemical structure of these hydrothermal carbons, and I also did back in time a lot of solid state NMR studies to try to understand what they are made for, you will see that they are mostly made of furane rings that are connected together, either conjugated together or linked by aliphatic linkers. They are also terminated with some oxygen-rich functionality, such as carboxylic groups or aldehyde groups. And you also have a smaller fraction of these long-range conjugated aromatic molecules. And the chemical structure you can tune by tuning the precursor and by tuning the temperature at which you do this hydrothermal carbonization, if you add a catalyst or not. So it's quite a tunable process. So the way this forms, for those that are chemists here, and I don't think I have a slide on this, is that basically let's assume you start with cellulose. The cellulose gets hydrolyzed to glucose molecules. This glucose molecule, we all know that they will isomerize to fructose. And then although you work in water, because of these subcritical conditions, hydrothermal conditions, you will turn fructose, into this molecule that is called 5-hydroxymethylfurfural, which is a furane ring here with a methyl on one side and a hydroxymethyl group on the other side. And so this molecule then starts condensed via all sorts of organic chemistry reactions and starts then dehydrated to form this furane-rich structure, and sometimes it really forms these conjugated molecules. So that's how the hydrothermal carbonization is happening. Now, again, these are, as you can see, very old papers. I just wanted to show that this can be used as a very nice functional materials for a lot of different applications, some of which applications that I know they're interested to bp-ICAM, and they're very cheap. So I thought I'd show this older work. So the nice thing is, as I said, you can add templates, you can nanostructure them, and because you have these functional rich groups on the surface of these hydrothermal carbons, you can functionalize them, for example, with amine groups, and then you can turn these amine groups into carboxylic acid groups. Then you can turn this carboxylic acid group even to more amines, or you could use the furane chemistry to really do Diels-Alder reactions onto the apparent structure of these materials. So now all these materials are made at low temperature. They're quite stable, but they're not conductive. So they're great for applications in water purification, for example, or in this paper, we have a porous carbon materials functionalized with a lot of branched amine groups, which are great at capturing CO2. This is some old work, as I said, we've never came back to it, but I would quite like to maybe come back to these concepts and start working maybe again on CO2 capture or direct air capture, but I never got around because meanwhile I got interested in batteries and electrocatalysis, and so I was always trying to make them conductive. Now, on how you make them conductive, as I said, you can make them at temperature as low as 180. And is this temperature, I show you that they are carbonaceous materials. They have all these furans, some aromatic groups, some aliphatic groups, some oxygen functionalities. So they're quite heterogeneous in their structure and not very conductive. But the nice thing is that you can take these carbons that you make at low temperature and you can nanostructure the way you want and carbonize them further. And you don't change the morphology. However, of course, you will change their microstructure. So you would go from something that is completely amorphous to something that is a hard carbon type material, something that is non-graphitizable, but you can have a lot of graphitic domains in it. So you could see the 002, the 100 peak. And you could follow now here nicely by NMR, as I showed you, the NMR of the material at low temperature have furans and aromatics and carboxylic groups and aliphatic groups. Excuse me. So as you carbonize them further, you would lose all these functionalities and you turn all the furans into aromatics and you have a more classical structure of a hard carbon that now is also conductive. So you could just make them conductive by heating them up. I would also like to add an advantage here of doing the hydrothermal carbonization first is the nice spherical morphology, the control of the structure, but also a much higher yield that you obtain by carbonizing a biomass precursor. Because if you just directly pyrolyze, you get some random irregular particles. It's hard to control the morphology, but also the yield is quite low. It's between 20 and 30% via direct pyrolysis, whether by doing this hydrothermal carbonization first, you locked already quite a lot of this carbon in the structure, so you can get yields up to 50%, which is much more economically viable. So again, these are some more pictures. This is my former postdoc, Shiori. Well, she was a PhD student with me. Shiori, she's now in Japan and ICE. And Robin White, who was a postdoc with me, he's now in Luxembourg Institute of Technology. And this is just to show that indeed, through using different soft, hard templating or in general material chemistry trick, you can really nanostructure these carbons to pretty much any morphology you want, from spheres to ordered pores to spherical pores, macropores, mesopores, hollow spheres, or even hollow tubes. And so this is very nice because you could already pre-tailor your morphology depending on which applications you would like, and I'll show you some examples. For instance, if you want to work in catalysis, you want something that has a high surface area and is porous as a support. If you want to work in batteries, you'd rather have something less porous or maybe with controlled pore size. Now, not only that you can do this carbon materials that are nicely nanostructured, but you can nicely combine this with the hydrothermal synthesis of inorganic materials. So again, these are still some pretty old results. This is my first PhD student, Rezan, in fact, who is now a professor in Turkey and Gebze Institute of Technology, and Jelena Popovic, who was also a PhD with me. She's also a professor in Stavanger University now in Norway. And you could see how you can nicely load, this is platinum nanoparticles supported on carbon that you do just in one step. You take a platinum precursor, glucose, do hydrothermal carbonization, platinum will be reduced in situ and deposited on these carbon materials. Now, if you want to play really at the more nanoscale with these materials, you can just put one single nanoparticle in the middle of a carbon holospheres by using some latex nanoparticles on which you just deposit one platinum nanoparticle, and it's a bit tricky to do that, and then you just coat it with carbon, and when you remove the latex, you form a holosphere with one platinum nanoparticle. This is a lithium iron phosphate mesocrystal that Jelena developed in her PhD for lithium ion batteries. This was about 20 years ago, but now lithium iron phosphate is becoming trendy again. So it's quite funny to see how the research trends are disappearing and coming back. And I've been in business for about 20 years, maybe even more interesting with people that have been even longer, but it's quite an interesting trend. These are some tin oxide nanoparticles coated with carbon. We also use this as an anode in batteries. This is a silicon nanoparticle that we coated with a conductive carbon layer and applied in lithium ion batteries to prevent this volumetric change. So anyway, these are some old nanostructures. Back in time in Germany, you were supposed to do a habilitation. Maybe some of you in the audience know what I'm talking about, and I didn't want to do it necessarily because you need to write a very thick thesis, but I was invited to write a book, and this became my habilitation. So this is something that came up from all this more fundamental research on carbon materials from hydrothermal processes. But in my group, we are still looking at these processes, and this is some more of a recent, two recent reviews from these hydrothermal processes to make carbons. And so if you're interested in this, you can have a look at these papers for a lot more details than what I said. So this is one way in which we produce carbon materials in my group. And as I said, we are using the carbohydrate-rich fraction of biomass, cellulose, hemicellulose, carbohydrates. But we all know that in lignocellulosic biomass, there's cellulose and there's lignin. So we have another process of producing carbon in our group, which is by taking the lignin fraction of the biomass and putting it through an electrospinner, where you apply very high voltages, and you form this Taylor coil, and then you have a random fiber formation that you collect on a current collector. So you spin lignin fibers, which we then carbonize to form carbon fibers. And so over the years, we've also been looking quite a lot at this technique, and we've been producing fibers that are completely disordered, more aligned, or we can even have rotating drums and align them in different directions where we gain a bit in mechanical properties. Now, we are not doing these carbon fibers to compete to, structural carbon fibers that are made from palm, because many people have tried, and my personal opinion is that nobody will ever succeed to beat polyacrylonitrile. But we are doing this to create flexible, freestanding, conductive carbon mats from more sustainable precursors for energy storage and electrocatalytic applications as supports. And so over the year, I had all these talented people that worked with me in the production of these carbon fibers with different properties, different pores. We could make them microporous, mesoporous, a combination of meso and micropores. We could, as I said, control a little bit their mechanical properties, and we've been applying them over the years a lot in energy storage applications, particular aqueous supercapacitors, but now we are moving more into batteries with this material. So Rob Hunter is still in my group, and all these other people are former PhD students and postdoc. They moved on to have important jobs in Europe and Australia as well. So I showed you that research in my group involves a lot of carbon materials, and that's something that we have a lot of expertise and we do quite a lot. But in terms of synthesis of materials, we also work with other things rather than carbon. We work with metal oxides, metals, even bimetallic or organic compounds. And so we do a lot of synthesis of nanomaterials, and we're trying to have this synthesis characterization theory test loop so that we understand their properties. And we work very applied. As I said, one part of my group does a lot of batteries, and we like batteries that go beyond lithium ion. So we work on sodium batteries, potassium batteries, aluminum dual batteries, recently anode-free batteries, lithium sulfur batteries, and we're still looking at silicon anodes for lithium ion batteries. So a combination of new and emerging battery chemistry and more beyond lithium, high performance, higher energy density applications. We also do a lot of electrocatalytic processes, in particular fuel cells and oxygen reduction reaction, but also oxygen evolution reaction. Clearly, we're working with bp-ICAM in the hydrogen project, but I'm also equally interested in CO2 reduction and biomass oxidation. And with my colleague Ivan Stevens, we're also working together on nitrogen reduction. Now, we are in a chemical engineering group. As you probably realize, I'm a chemist by training, but it's nice working in an engineering department because you get to really think about whether it makes sense or not from the very start, because we have very talented researchers that I collaborate with doing life cycle assessment and process engineering. So, for example, recently we published a paper looking whether really platinum or platinum-free catalysts for fuel cells, which ones are more sustainable and which one makes sense. And we also have been doing a techno-economical assessment of biomass electrolysis, and also we constantly do techno-economics of batteries. I will show you some of these results if I have time. And maybe what is next for me is I'm very interested in these high throughput techniques. In particular, high throughput applies to batteries and electrocatalysis, and I was lucky enough to get a strategic equipment grant from EPSRC called DigiBot. However, we are now expanding this to DigiCut, and we are going to get, and I promise that lots of people from BP will be invited to the launch of these centers. We're going to get robots, one robot that will be able to synthesize energy materials in high throughput, with a robot arm that will be able to place things in a furnace automatically, so it could do high temperature energy materials. We will get a robot that would take these materials and assemble them together in coin cell without any human intervention. Well, we don't know that yet, but hopefully little human intervention. But I'm very interested in setting up a electrocatalysis lab that will happen in high throughput and will look more at gas diffusion electrodes and membrane electrode assembling rather than model system, where you could do a lot of reactions in parallel and try to figure out first which are the best conditions, and then maybe go down from there to understand the fundamentals. So today I will try to tell you about three things if I have time. One is on my recent interest in biomass electrooxidation to produce hydrogen and chemicals. The other topic is on single atom catalyst. There is some research that's been doing in my group over quite some last years, but I'll present you the latest results. And if I have time, I'll tell you a little bit about sodium ion batteries as well. So yeah, I don't need to probably tell this audience the hydrogen comes in many colors and is a very important energy vector for the UK, which will be used to decarbonize our economy across all sectors. And then normally, of course, we produce green hydrogen from water electrolysis, and depending on the type of water electrolysis, depending on the type of the, let's say, electrolyte in between, you could have different types of water electrolysis, out of which maybe this proton exchange membrane electrolysis is the most efficient one. So now if you look in PEM electrolyzers, you would see that basically you have an Nafion membrane here, you have normally an iridium oxide catalyst for oxygen evolution reaction, which is supported on a porous titanium transport layer. And on the other side, where you evolve the hydrogen, you have platinum on carbon. And you would see that the most inefficiencies in this process come indeed from the oxygen evolution reaction, where you need to use quite significant amounts of iridium catalyst and you still have quite high of a potential, which is not so much the case for the hydrogen evolution. You need very little platinum in particular for PAM, so this isn't a problem. So my take on this, of course, as I said, within the hydrogen bp-ICAM project, we're looking at understanding better these processes in trying to make this iridium oxide more efficient and maybe partially replace them with other things. But another take that I have on this is, do we really need to electrolyze water, or could we actually electrolyze other things that have protons? And you know that I love biomass in general. So one idea is, why don't we electrolyze biomass? And so if you do that, instead of oxygen evolution reaction here at the anode, we could convert this biomass to high value chemicals, because we would just partially oxidize it. And when we do this, we would get protons that will be converted here at the cathode, where you would still have hydrogen evolution and formation of hydrogen. So there are advantages of doing this, in particular that these oxidations are happening at lower potentials compared to oxidizing water. And so that's one advantage that would overall lower the cost of hydrogen coming from these processes, but also, and our techno-economical assessment showed that this is actually the biggest value, you could actually have greener manufacturing processes for commodity chemicals, should you control the selectivity well enough. So we've started looking at glycerol oxidation, and we've started looking at the fundamentals of the reaction mechanism on platinum carbon, and also on more non-critical elements. But of course, you can't have everything in life. So the more you get to non-critical elements, the higher the potential at which glycerol oxidation happens, and also the selectivity to, like, maybe free carbon products, which is something that we would like, decreases quite a lot compared to platinum. But saying that, platinum is also very easily poisoned in these reactions. So to avoid this poisoning, we thought maybe we could try to add some nickel atoms to platinum. So this is Hui Luo, who was also a former postdoc of mine, who started all this research, who's now a lecturer at University of Surrey, and we are still collaborating very closely on this topic of biomass oxidation. So basically, she added some nickel to platinum, and so that I don't want to go through the details, but we had and compare the pure platinum catalyst, a catalyst where we would have an excess of platinum atoms to nickel, a catalyst where we've managed to have one platinum near one nickel atoms, and another catalyst where we had an excess of nickel. And you would see here the selectivity to glycolate, where you would see that the higher the nickel content, depending on the potential, you change the selectivity. And that's because the way these intermediates get absorbed, the more nickel you have, the more you absorb them via, let's say, all free carbons, and you get directly to carbonate. So we try to elucidate the mechanism of this reaction. And because if you look at this graph here, you would see that it's actually quite advantageous to have one platinum near one nickel, and we have a lot of characterization to prove this XF and XPS and ICP-MS and XRD, but I don't have time to show you all of this, but this is published here in this paper. So this material, platinum nickel 2, where I said there is one platinum near one nickel atom, you would see that has the highest mass activity and also the highest specific activity. So we selected this material to look in operando with SAINS at ECRF and diamond lysors to really understand better the mechanism through which this catalyzes the glycerol oxidation. And very interestingly, because first we thought, if we would have a platinum atom and a nickel atom, that we would have independent OH and carbon intermediates adsorbed on these different sites. And so we wanted to see if that would be the case. But in fact, we've seen that that's not the case. And we've seen, very interestingly, that also when we work in the absence of glycerol, we really oxidize the nickel all the way to nickel oxyhydroxide while doing this, while the OH adsorption is happening. And this is nicely confirmed by SANE and also spectroelectrochemistry that we did in the group of James Duran. And you really see how this nickel hydroxide islands that you would form anyway onto the surface of this platinum nickel goes all the way to nickel oxyhydroxide during the anodic step. But when you work in the presence of glycerol, you have such a strong interaction between the molecules on the surface and nickel that this actually prevents further oxidation of nickel and more positive potential, and there is no optical adsorption change. It's a very nice correlation between SANES and spectroelectrochemistry here. But the bottleneck here, that no matter if you work on which catalyst you work, as I said, platinum gets poisoned quite easily. Platinum nickel 2 shows the highest partial current density and Faradaic efficiency to tatonate, and platinum nickel free, so the more nickel you have, the more you cleaved more carbon bonds and you get to C2 products, but it's very difficult to control the selectivity within these processes. So then we took a step back from this mechanistic study and we went more with the chemical engineering hat and thought, what do we want from this process? Because clearly making all this mixture of organic acids in water via glycerol oxidation is not such a good value in terms of technoeconomics, because the hydrogen that you produce, you will never get to the same scale with water electrolysis. So the advantage here is that you produce some high value chemicals and some hydrogen at the side that you might use in decentralized applications. And we wanted to make something selectively. And so we looked at the market size for glycerol derivatives in terms of market price and market size, and came up with the idea that would be really nice if we could actually make lactic acid from glycerol. And so we knew that we have a pure electrochemical step, which I just showed you previously on platinum and platinum nickel, where basically you get from glycerol to glyceraldehyde, which then is oxidized to glyceric acid, tartonic acid, glycolic acid, and so on. And I showed you that it's actually hard to control the selectivity. However, from thermal catalysis literature, we've learned that if you could actually just turn glycerol into dihydroxyacetone, and then this dihydroxyacetone will further dehydrate to form this 2-hydroxyacrylaldehyde, which is in equilibrium with pyruvaldehyde. And because we are in an alkaline environment, this will rearrange to lactic acid. So we thought, how could we actually promote the path in red? With our collaborator from DTU, we did some DFT calculation, and we've seen that indeed there is a pure electrochemical path, but there is also a mixed electrochemical and chemical path to lactic acid. And what we learn is that we could actually, looking in the literature, we could actually use platinum as the electrocatalyst to form dihydroxyacetone, and we could support this platinum on carbon, that it's a commercial catalyst, onto a support that has a lot of Lewis acid sites. And by having a lot of Lewis acid sites, this Lewis acid sites will actually promote the dihydroxyacetone conversion directly into pyruvaldehyde. So basically, you will prevent the glyceraldehyde electrochemical step. So the platinum will just do glycerol to dihydroxyacetone, and then the Lewis acids will then go from dihydroxyacetone to pyruvaldehyde, and pyruvaldehyde will then form lactic acid. And so that was also the idea of Hui. And in fact, it worked. So we looked at the pure carbon and we looked at the platinum supported on pure carbon black, but then also on cerium, titanium, and aluminium. And we correlated the surface acidity density of all these supports with the lactic acid production. And we've seen a very linear correlation, which is also confirmed by DFT if we looked at the production of dihydroxyacetone on alumina, which has the acid sites. We could see also this very nice correlation. So based on this, we have actually succeeded to selectively, or more or less selectively, I would say quite high selectivity in the literature, select glycerol to lactic acid through a mixed electrochemical and chemical path, while on the other side we've happily evolved hydrogen, and because of the lower potential at which the biomass, the glycerol oxidation happens, we have a very good energy efficiency of 26 versus 51 kilowatts per kilowatts hour per kilogram of hydrogen. So this is with water electrolysis, and this is with our process. And so this is something that we're doing. We are also working on other oxidation reactions from glycerol. In particular, one exciting development is trying to use PET directly to depolymerize it through an electrochemical pathway to terephthalic acid and ethylene glycol, which are its monomer. And we can go one step further and convert this ethylene glycol through glycolic acid, which is a very nice cosmetic from your skin, and hydrogen. We are also working on oxidizing hydroxymethylfurfuryl to furan decarboxylic acid, which is a nice monomer of making a polyethylene furanoate, which is a bio-based version to PET. And in all these electrooxidations, we are aiming to maximize current density and selectivity and produce green hydrogen on the side as well. I think I'm running kind of out of time, so because I've talked to you about hydrogen to chemicals, I might skip the single atom catalyst part, and I will tell you something about our work on sodium ion batteries. And so I think I will do that. So now you have to bear with me skipping all the oxygen reduction slides, but I'll be happy to talk to you, anyone that's interested in these single atom catalysts as catalysts for fuel cells. And in particular, what we're doing here, we are trying to do a lot of degradation studies to understand how these more sustainable alternatives to platinum are degrading. But as I said, I don't have time to talk about this today, and I'll skip through the batteries. So we all know that we have a big problem with lithium-ion batteries based on the critical materials, and everyone is trying, well, everyone. There's big incentives to look beyond lithium, and in particular beyond materials that are critical into batteries. Oops. So diversifying batteries beyond lithium ion is something that I'm very interested about, and we recently wrote, well, it's not so more recently anymore, it's been 2 years ago, this perspective in this journal One Earth on our perspective of how this is best to be done. And we also gave a definition to what, in our opinion, a green battery is, and we've looked at different technologies, and we give them based on our personal opinion, based on what we know and what we've seen commercially and scientifically, time to commercialization. And as you see back in time, we gave sodium ions less than 5 years to the market. So that was 2022. So basically we now have 3 years for sodium ion batteries to get into the market. And I think we were right, and we weren't exaggerating. And so talking about books, we've also edited very recently, last year now, a book which has 2 volumes on sodium ion batteries. And why people are interested in sodium is clearly that it's more abundant than lithium. that you don't have to change anything in the manufacturing of your battery, same equipment and everything the same. And also potentially you can have cathodes that are completely free of critical materials. You can have also cathodes with some critical materials, and the problem is the material criticality is changing each year and depends a lot on geopolitics. So, when research on sodium-ion batteries started, nickel wasn't critical, and neither manganese, but now they're both critical. But you could have Prussian blue analogs that have absolutely no critical element on this. Sorry, my computer is very slow. So, talking about sodium-ion batteries and commercialization, there are several companies around the world that are quite advanced with sodium-ion batteries on the market. Now, of course, we all know that it started in the UK with Faradion. They did fantastic research, and then they took it all to India, and they still have research facilities here. And the plans are to build a big gigafactory for sodium-ion batteries in India. There is a company in France as well called Tiamat. They are also working on sodium-ion batteries. They've recently released a product on the market that is powered by sodium-ion batteries, which is this screwdriver that has a very nice book about LCA between sodium and lithium-ion batteries. Now there's the big giants, KTL. They keep announcing that they'll go commercial with the sodium-ion batteries with about 160 watts hour per kilogram. They would charge in 16 minutes. And they announced this in 2023, but nothing happened. And we are in the middle of 2024, so we're still waiting. And so, interestingly, the International Sodium-Ion Battery Conference last year was in China, and it was by organized by one of my close friend and collaborator that I know from Germany, Yongsheng Hu. And Yongsheng is the CEO of this Haina battery, who are actually already having sodium-ion batteries cars, and I had the pleasure to ride in one of the sodium-ion battery cars. They're no license yet to go on the streets, but you can drive them around the campus, and they feel exactly like a lithium-ion battery, but I didn't drive them that long to make a comparison on how much they last. They also have this very nice storage facility. Now there's also Natron Energy in US. They're using sodium-ion batteries for data storage and also for this type of pooling vehicles for aeroplanes and so on. Now, interestingly, if you look at all these battery companies for sodium-ion batteries, they all use a different cathodes. Faradion use a mixed layered oxide. There is a mixture of prismatic and autohedral. Tiamat uses NVP, which is sodium vanadium phosphate. KATL is using a Prussian white. Haina is also using a layered oxide, and Natron Energy is also using a Prussian white. But if you look at the anode that they're using, they're all using hard carbon. But the question is, what is this hard carbon? And you know that I do love carbons. And people think that hard carbon is the same thing every time, and you can just burn some biomass precursor or organic precursor and you'll get your ideal hard carbon. But actually it's much more complicated than this, and I think we have very good cathodes on the market, but the limited step is still these hard carbons. And of course all the companies are rather secretive about their hard carbons, but I know that there's a struggle on the market with hard carbons. So if lithium and potassium go into graphite, sodium cannot, but very happily goes into a hard carbon, which has this type of disordered structure. And hard carbons are complicated. And in order to really understand the best hard carbon for sodium storage, you really need to understand it atom by atom and how sodium stores into this carbon. So that's what we've been doing for a very long time. We've been looking how each of these parameters in the hard carbon, the average graphene layer, the interlayer spacing, the atomic distances, the curvatures, the pore diameter, the functional groups are really affecting the sodium storage mechanism into these hard carbons. Again, I'm coming to the end, so I won't have time to give the details, but it's all published in this paper. we're using our hydrothermal synthesis to turn, in this case, glucose into hard carbon. Hydrothermally, we get the spherical particles, which then we carbonize further, and we carbonize them between 1000 and 1900, so that we could do a lot of atomistic characterization and modeling to really understand the sodium storage mechanism into carbon. So making a very long story short is that we looked at electrochemistry, we looked at ideal interlayer spacing, we looked at the pore size, we looked at the defects and oxygen content, we went a lot to synchrotron, and we've realized that in order to have the best possible hard carbon, you need to have an interlayer spacing between these disordered graphene layers of about between 3.6 and 3.7. You need to have, well, this is more complicated with the pore. In our case, the best material proved to have pores of 2 nanometers, but they are the microstructure and the pore are closely related. And you also want a sweet spot on oxygen functionalities, or actually other types of functionality, so that the sodium interacts with these defects. And so, as I said, we did this by a number of techniques, including inoperando NMR, PDF analysis, X-ray adsorption. And just to tell you, the conclusion is that you want to be in this situation here, where basically if you have very big disorder, carbon sodium randomly adsorbs on it, but you'll have very poor irreversible capacity. Now, the ideal case is where you have some pores, and in this plateau, sodium goes and sits in the pores. But in order for sodium to go to these pores, you need to have the right interlayer spacing so the sodium penetrates to this pore. You can have very big pores, but if your interlayer spacing and graphitization is too high, sodium cannot go in and access this pore. So ideally, to make the ideal carbon, you need a combination of heteroatoms, interlayer spacing within a very sweet spot, and then pores where sodium goes and plays, and metallic sodium. So this is now something that we are trying to take to the next level, and we are doing cell with commercially available cathodes in the literature, and we have very impressive performance for our hard carbons, where we managed to cycle them for 3,000 cycles, and we still retain a capacity of 300 milliamp hour per gram in a full pouch single layer cell. And the nice thing is that we can fast charge these carbon materials as well. So you see that only basically in 4.3 minutes we can still reach above 200 milliamp hour per gram. And that's because we really took a lot of time to really understand the fundamentals, and now we're trying to go to scale. And just to say, the interface is a very big problem that we're also trying to understand in these hard carbon materials. And I think I need to really go to an end of my presentation. I had probably way too many slides, but I hope I gave you a flavor at least of our carbon materials as a whole, our technique of oxidizing biomass to high-value chemicals and hydrogen, and we're big fans of sodium-ion batteries, but that's not the only technology in batteries that we're working for. So I'd like to thank all the funders and my wonderful group of people, and thank you for your attention, and I hope we still have some time for questions.